Sir, we'll for,
yeah, start. Yeah, sure. Yeah, sure. Normally, how many people are expected? Now we have 18.
60 plus are attending, sir.
60. Oh, good.
But some are joining a little bit late. They are attending to their regular duties. So
Yeah.
But within 5 minutes, we'll have around 40 participants.
No problem.
We'll start then and slowly remaining
Sure.
like that.
Yeah,
And some more are watching on YouTube also.
Oh, okay.
YouTube live streaming is also there.
Yeah.
Being faculty development program, the only faculty members and practicing engineers and few research scholars are attending.
Research scholars are okay, no?
Research scholars are attending.
Yeah, that's good.
PG students and other students, we are not allowing. Sir.
Oh, that's
good. Given the
becomes...
links so that they can watch on YouTube live stream.
Okay.
So this is a second FTP program, sir, on shallow and deep foundations.
Okay.
Actually, AICT has sanctioned. We have applied for this before COVID period.
Okay.
When it was sanctioned, COVID lockdown was there, and the AICT has suggested to organize the event 2 times.
Okay.
So January last week we had one program for 15 days. Okay. So this is the second one, sir. And the participant who attended first program cannot be participant this time.
Okay.
But still some out of interest are attending, we are allowing. Separate set of participants are required as per AIC.
No, I know IAC how it's working. It's not, there's a lot of confusion. So I know.
Sir, we'll start, sir.
Yeah,
So,
sure. Yeah, sure. Yeah.
So, good afternoon to all of you, and welcome to the afternoon session of Faculty Development Program on Shallow and Deep Foundations, being organized under AICT Quality Improvement Scheme and the Department of Civil Engineering and the University College of Engineering. So, I hope all of you are enjoying the sessions, and during this session we will be having one more interesting lecture on reliability based design approach for foundations by Professor G.L. Shivkumar Babu. Though most of you may be knowing about Professor G.L. Shivkumar Babu, but still as a formality and for those from other than Geotechnical Engineering stream, I'll present a brief biodata of him. Professor Shivkumar Babu is graduated from Sri Venkateswara University, Tirupati in the year 1983 and obtained his master's degree in soil mechanics and foundation engineering from Anna University, Madras in 1987. And after that, he has pursued his doctoral work at Indian Institute of Science, Bangalore, and obtained his PhD in the year 1991. He worked as a Humboldt Fellow in Germany during the period June 1999 to July 2000, and as visiting scholar at Purdue University, USA during February 1995 to February 1996. He is serving as chairman of International Technical Committee TC 302 on Forensic Geotechnical Engineering of International Society for Soil Mechanics and Geotechnical Engineering. He has served as the president of Indian Geotechnical Society for 4 years during the period 2017 to 2020. So under his dynamic leadership, we have organized a number of significant events, and very recently during December, we have successfully organized online Indian Geotechnical Conference 2020 under his able guidance, and he is instrumental in starting IGS student chapters at many places in several engineering colleges. He is a fellow of American Society for Civil Engineers, Civil Engineers, and is also serving as a governor, ASCE Region 10. He has guided 17 PhD and 5 MS research scholars, and guided several MTech dissertations. He authored a book on soil reinforcement and geosynthetics, which most of you may be referring for your PG coursework, and for those who are working in the area of info soil structures. He has edited 8 books and proceedings, and has several publications. You will be surprised to know SAR has more than 180 published papers in reputed national and international journals. And in addition, he has 130 more papers published in proceedings of conference. In all, he has more than 300 publications. He has received several awards such as John Booker Award from IAC MAG, Humboldt Fellowship from Germany, DST Bioscast Fellowship, and a few awards for the best papers from Indian Geotechnical Society and American Society of Civil Engineers. So he's one of the topmost experts in the field of geotechnical engineering, not only in India, but also internationally. And he keeps regularly organizing international conference on forensic geotechnical engineering. So with this brief introduction, I invite Professor G.L. Shivkumar Babu sir to deliver his lecture. Please, sir.
Thank you, Professor Reddy, for a very nice introduction. I'm always happy to give any lectures, any programs whenever you're associated with, particularly, and you're all very kind, and particularly the audience, you always have an excellent audience. You do a lot of efforts. So I would like to now share my presentation. Is it okay? Yeah, just on the entire screen. Okay. Let me just see. Where is that? Present now. Okay. Is it visible? Okay. I hope it's visible.
Yes, sir.
Okay. Thank you. First of all, I must thank the organizers, particularly Professor Reddy, for giving me an opportunity, and I would like to thank all the participants here. The topic that I would be talking would be on reliability analysis, which is very important in all the branches of engineering, and more so in geotechnical engineering, because we always deal with factors of safety and we call them as factors of ignorance. But I think that stage is now we have to be replaced by a stage of knowledge, where knowledge-driven design methods are there. That's very important when people are talking about machine learning, data analytics, and all of that. So this is where, in a nutshell, I would like to give some presentation on how we can do things based on reliability analysis. I think you know about Carl Terzaghi, the father of soil mechanics, who says that the soils are made by nature and not by man. So whenever you move from a product, the manufactured products like steel and concrete, as civil engineers, we deal with them. The theory that we have we have some theories, but then, they're not really complete when it comes to soil. Because, say, for example, the soil is uniform, homogeneous. Maybe you can say for concrete and steel, but it's not valid for soils. Nevertheless, you have to make some design decisions. So because the properties do change from point to point, and we cannot spend a lot of money. And so there are a lot of issues here. So how do you handle this is a question. So that is the reason why you use factors of safety in our engineering, geotechnical or water resources anyway. But to what extent we can really demystify this thing is something that we need to understand. And see, variability is there everywhere, so variability, if everything is there, particularly natural phenomena. So we call them as natural variability. So maybe it in temperature, climate, everywhere it is there. In soils also it is there. We call it as inherent variability, like general soil profile, point to point, there could be variations. Even in sun rises every day in different times, and over a period of one year, it could be different, like that. So there is a inherent variability, maybe 10%, 20% or something. There could be always some variations. How much is that variation is one thing one should understand. And that is called aleatory uncertainty. The second thing is epistemic uncertainty. This is about, it's very important, because the proper lack of knowledge, or even lack of complete understanding of the whole thing, in the sense that even you apply some models. Say, for example, I can give an example that we idealize. Say we say that the soil is uniform, or concrete is uniform, and all of that. So we use some design calculations, whether it is for theory of bending or bearing capacity or pile load capacity. We use simple methods, assuming that there is that earth pressure is acting like this. Then you calculate the passive resistance or active resistance, or whatever active conditions. All of that we assume, and then make some calculations. So that is called, because, but then it may not be, we don't know. So exact behavior we don't know. So that is called epistemic uncertainty. We assume simplified mechanisms that you can follow, you can understand. Because again, if the methods become complicated, it's difficult to practice. So that is an input, because for a regular engineering practice, we need to have simple methods of calculations. It should not be too complicated also. That is another requirement that we should do. But then, you're trying to simplify the complex process that we should understand. So that is called epistemic, or called model variability, or transformation variability. Like model variability is that, like we apply a model, there is a variability. What is transformation variability? Like, say, for example, you do some test in the, for example, SPT test we do in the field. Then you convert it into friction angle, or you convert it into something else, skin friction, or N values are related to in so many ways. So that is, you're trying to equate something to something, and something unknown, something, something, measure something, then, but you don't know other property. You try to get some equations, and most of the times we use some equations that are available in some books. We never got them validated to our conditions. So it's called transformation uncertainty, and we are not sure to what extent they're correct. The other problem that we have is measurement variability. The thing is that whatever you do in the lab test or field test, there is always a variability, because because of the testing, very precise testing, the tools and all that, there is a variability. Particularly the issue is that in soils, it's a grains distribution. It is so variable. When you try to measure a quantity, the grains distribution of points that are in contact with the test condition will affect the design. So whenever you do measurements, there will always be a measurement variability. So you can say that the soil is inherently variable. So in situ measurements, transformation variability is there. Then, so you have an estimated property. Yes.
Sir, slides are not moving, sir.
Is it moving now?
No, sir.
Now, okay. So so I know the solution is that you use now.
Yeah. Now
Okay.
it has come.
Yeah. Okay. So the variability is different types.
Also,
Yeah.
sir. Make it full screen.
Yeah. Now is okay.
No, sir.
Now it's, so actually in a normal screen it is it
Okay,
visible? Sir. Variability, and if I make it full screen, is it visible? I'm just trying to move the slides. Is it very visible? No.
Sorry, you put it in slideshow mode and
okay.
share the entire screen.
Right. Is this slide visible? Variability models. The heading is variability.
Slide is visible, sir.
Okay. So the other thing is that the one important thing that we see in soils is that there is we call it as a scale of fluctuation. So we have this sort of, we know that it's variable. The moment you say it's variable, we call it as a random variable. And the random variables means it has a mean value, it has a standard deviation. So if you know the mean value and standard deviation, then we have a knowledge available from probability and statistics. We can use that. So for example, in an engineering sense, you have cohesion values and friction values. All of them are variable. So for example, you have 10 cohesion values, 10 friction angle values, and you want to find out bearing capacity. Bearing capacity also will have 10 numbers, so it can be even 100 numbers. So it can be numbers, and so they're all variable, which is actually a fact. But then if you want to, so the factor of safety itself is variable, and so we want a factor of safety such that its factor of safety is always more than 1. What is the probability that the factor of safety is more than 1? If it is 95% of the times, say for example, if you have 100 calculations and 95% of the time you get factor of safety more than 1, It only shows that the reliability is 90 or 95%. So that is one thing. The other thing that happens in our practice is that the properties are, for some distance, they are all well correlated. Like if you take samples at, suppose there is a soil is uniform, it only means that you take sample here or maybe 10 meters away or 100 meters away, you will get the same property, right? So that is called uniformity. And even, okay, isotropy and anisotropy, that also you know that the, say along depth or along width or along X, Y, Z directions, if they're different, we call it as anisotropic. But for simplicity, we assume them as isotropic. But then, these properties are variable both in the vertical direction, the horizontal direction. That's what we see. And these are also limited to some distances. Like I can give an example of a thing that, say there is a deposition of a river, and then up to maybe 10 meters, the properties are same. After 10 meters, they'll be different. After next 10 meters, they'll be different. So what it means is that is because they are all, sediments because of a river flow. And when there is a different velocities at different stretches, the sediments will be different grains distributions will be there, and they give correspondingly fundamentally a different behavior. So that is called random feed, so because that is how things happen, and that we call it a scale of fluctuation. So what it means is that if the soil deposit is truly random, so you will have a mean value and standard deviation. That's enough. But if you say random field, it will have what is called autocorrelation distance, like 10 meters or 20 meters. Like this can be measured. This can be even calculated. There is a method of calculation to what extent this is random. I'll give an example here. We call it as autocorrelation distance. Like I hope you're able to see one figure here, autocorrelation distance. I hope you're able to see that. Yes. So if the properties, if you take samples at two locations and if they're at a close distance, they're well correlated. So well correlated means the correlation between them is 1. But as you take one sample here and take another sample at 10 meters, there will not be much correlation. So the correlation becomes 0, and that distance at which the correlation becomes very, very minimum is called autocorrelation distance. Say it can be a 5 meters, 10 meters. But the idea of uniformity is that even at large scales, the properties are same, right? So that is that thing. And so autocorrelation distance can be anything to anything that should be measured. And that is possible by samples, or there are some standard guidelines on this. What we do, actually, I will generally give some general idea of the reliability analysis and also show some applications to shallow and deep foundations, and also take some more, till the time permits, we can discuss. So the reliability analysis is very, very important, because in structural engineering, they do that. They use what is called LRFD design, like loads are increased, resistances are decreased. So that we call it. And reliability analysis is required in all the types of buildings, transportation facilities, structures, everywhere, landfills, and all of that. And more important thing is, why would you go for reliability based design? Whether it is a shallow foundation, deep foundations, and all of that, the design procedures need to be good. Otherwise, like if you go to Federal Highway or even UK codes of practice, the foundation design is based on LRFD in US. Okay, and even in Eurocode, it talks about partial load, partial factors. But in India, we are not doing anything, and that is a very dangerous trend, because you have a building which is with LR, you have a bridge, say for example, you will be knowing that a lot of bridge designs are done, and they are based on LRFD. Some level, in fact, even in IRC, they didn't understand too much, but they are trying to understand these concepts a little bit and use them. But foundations are working stress method, which is actually a very serious concern, because there is a design inconsistency there. You design based on some methods at the top, some cases, and something else, and some other philosophy. Like, it is very difficult to judge which is correct. Like, you take medicines for Ayurveda, you can take homeopathy, same thing, like that. You keep on taking all sorts of allopathy, all sorts of things, or even it's like you have a design inconsistency. It's very difficult to understand the process. So infrastructure needs better design procedures, and then there are a lot of natural causes like hurricanes, floods, tornadoes, and why? Because the reliability. See, these are all highly variable. We know that. So you have to design for 10-year return period, or 50-year return period, or 100-year return period. Whether it is earthquakes, landslides, rainfall induced problems, you have to have some sort of statistics. Otherwise, it will be very difficult to justify the cost. Like if somebody says that what is the design life of the structure? Is it 50 years or 20 years or 100 years? Like we have seen, say for example, the roads. You say the design life is 15 years, but we have seen our roads within 6 months, they're not there. So what it means is that a lot of there are a lot of issues. Even man-made causes can be there, like poor maintenance, vehicle collisions. Main thing is the limited available resources. So the important thing in this reliability-based design is that you can optimize things. You can optimize things, and say if you have this much of investment to make, the failure will reduce to this level. That understanding is possible to give. So what is important is that in reliability analysis, we should understand the causes of uncertainty. Load models, I was just mentioning about loads like earthquake loads, rainfall. So there is a load pattern, right? So our load combinations, like you have to understand this load models, whether it's for shallow foundation, say for example, a pile foundation design. So there could be not only so in a riverbed, what are the lateral loads, what are the vertical loads, then any other loads due to erosion, erosional failure. There could be many things that can happen. So we have to understand the load models, then resistance. So then once you understand the loads, we know that you can always, you'll understand the load is coming in a frequency of 10 years or 15 years or 20 years or 100 years. So you'll know what are the load factors. You can calculate the load factors also. Then you also have resistance factors. What is that? How much of resistance is given by your structure? Like, whether it is a beam or a column or a shallow foundation or a deep foundation, like along a failure surface, what is the resistance? So if the resistance, like it is also variable, as we just discussed. And so what is the equation for resistance? Are you using a simple planar surface? Are you using a log spiral method? Or are you using something else, or trying to put a reinforced soil technique? So all of that can be there. That gives a resistance model. So once you know the loads and resistances, their methods, then as I said, the loads can be highly variable. So we know that. So resistance are also variable, and you try to calculate factors of safety in all these. Say for example, 100 cases wherein loads and resistances. And our objective is to see that always loads are more, the resistances are more than the loads, right? So that the factor of safety is more than 1. So we make sure that the resistance is more than the loads for 95% of the situation, or 90% of the situations, which means that the reliability is 90%. That is called reliability analysis. Simple as that. And what is target reliability? So the thing is, as I said, I just mentioned 90%, 95%. That is what is called target reliability. Like we don't want 50%, right? 50% is like factor of safety equal to 1. I cannot say whether if the factor of safety is 1, can I say anything? We cannot say anything, because a failure probability is 50-50. If the factor of safety is 1.5, can I say anything? I cannot say anything, because we don't know about how much of factor of safety variability is there. So that's very important. And so design guidelines are based on this. As I said, federal highway guidelines are based on this, codes are based on this. But in India, I think whether you take IRC codes, whether it is IS codes, I think unfortunately many of them are not aware of them. And a little bit effort was made by some professors, I should say only from, again, Andhra University professor, senior professors were there earlier, Professor Dayaratnam. He did, he was from IIT Kanpur, and he did little on this, but more into structural side. But then, again, in a committee, you'll have 10 people. So ideally, they should have done 100% work. So you'll only do 10% work or 15% work. So that is a problem. So, like I just mentioned, why is this required? Concrete variation can be 10 to 8%, short columns 15%, steel member 10%, aluminum. They're all, concrete, steel, aluminum are controlled condition. Whereas you come to soil, the coefficient of variation, what is this number percentage is the standard deviation by the mean value. If the standard deviation is some number, like whether it can be compressive strength or shear strength or whatever. So they're all highly variable. You can see that they are very, very variable in soils or even in concrete. That's why they do LRFD, which means that we have a strong reasons to use some of these methods. And what
Sorry
about
for
low?
the interruption, sir.
Yeah.
Slides are not moving again.
Which slide you didn't? Okay.
Actually, slide is at 4th. Only 4th slide is visible, sir.
Okay. Yeah, you're able to listen. No? These are okay. Yeah. Now you're able to see this number. This one you are able to see. Okay.
Yes,
so
thank you,
of course, these 3 slides are more about general thing which you must have heard. And okay, I can just quickly go through the third. See, you have load need for reliability based design is very important because most of them are variable loads and resistances. So reliability analysis is important. The motivation is that the variability is there in soils and concrete everywhere. So you can't have just an arbitrary factor one or whatever you want. It is not correct. You have to come based on this reliability analysis, and particularly the loads are high. I just mentioned about aleatory uncertainty, epistemic uncertainty already, right? So all these things, as I just mentioned, are random variables. So like we don't want, as I said, capacity should be more than the demand or resistance should be more than the load. You're able to see this figure, very important figure, right? I hope you are able to see this figure. Hello?
Yes, sir. It is
okay.
visible, sir.
Yeah. So the thing is that we want the capacity should be more than the demand, but how much it should be more? Like how much should be theoretical? No, that's what I mentioned. So we normally provide more than 1.5, 2. The factor of safety is as high as 5 or 10 because we don't know about the design methods properly. I will show you that. And so the issue is that is where we are going to address that issue. That is what I want to say. And the other thing is most of the time in when you are trying to predict something, you should be able to, you have a theoretical model and prediction. So it should be reasonably correct. So you use an equation for pile load capacity, or you have a equation for bearing capacity, and then you do a test. So there should be reasonably correct. So there are some different conditions. We call it as unreliable and invalid, which we don't want. Unreliable but valid means, but there is a lot of errors associated with that, like an SPT test. Okay, this is an example of an SPT test. Reliable but not valid. There is always a bias. Say, for example, we know that there is always a 10% extra. What you can use the equation, but it's always 20% extra. So we call it as bias. So it's reliable only, but you know what is a bias. So you correct it for bias. How do you correct it for bias? We know that it predicts at least all the time 20% more. So now you know that number 20%, and its mean value and standard deviation of bias you calculate. Then once you know the standard deviation mean value of bias, then that you can bring it down to proper number. So both reliable and valid is something hitting the target. Again, a reasonable, it should not be too much errors, like 10%, more than 10% or 5% in other engineering like mechanical and other things. So you don't accept them. But unfortunately in soils, they're all natural variable. In civil engineering, we accept because the variability is high. Because one important thing is there is always a probability of failure, and probability of failure can never be 0. But in manufacturing, like mechanical and electronics and all of that, they try to reduce the probability to the very, very low levels. Okay. Say like they use what is that 6 sigma and all of that, right? So the 3 sigma rules we know, like based on normal distribution. And the rule is that design codes must have always a rational factor of safety. It should not be too expensive, or it should not be too many failures. So we need to do a reliability analysis. That's what we'll do. And the reliability analysis is the probability that the structure will perform its function during the predetermined lifetime, whereas the risk is opposite. Risk is also in terms of the failure consequences. Like, say, for example, there is a sea erosion or anything, and what are the impacts. So you need to look at even how many people are affected, all of that, particularly in environmental engineering and other things. And other problem is that the risk approach is not rational. That one thing, what is risk to you is not risk to somebody else. So, and then because of that, risk perception is different. Like earthquake, you have a lot of weightage to earthquake failures and flood failures, but poor maintenance, we don't care. I mean, at least in Indian context. So there are so many things. So risk perception needs to be rational and then uniform. So we'll discuss how to measure risk or reliability, how to incorporate risk in or reliability in practice, and how do you design this infrastructure systems for risk, whether it is a road, whether it is a pile foundation. The philosophy is same, and how to upgrade the existing infrastructure to have a certain reliability. Because if you go to World Bank or the ADB, Asian Development Bank rules, they say that you have to do so much, otherwise your project, you'll not get the projects. So that's what we'll see. And so as I said, in loads and resistances, right? Loads and resistances. Load has certain parameters. So, for example, wind load or the wave loads. So it has wave load. What is the speed? What is the load? It has some equation, right? And earthquake also, it has earthquake loads. It has a maximum credible list that that all the parameters of the earthquake, like all that we should have. And resistance parameters is what resistance parameters also you need to have C, phi, gamma, then what modulus, all of that are resistance parameters, right? So we try to formulate a limit state function. Actually, factor of safety is a limit state function, because factor of safety equal to 1 is called limit state. That is called the state of failure. And we don't want so factor of safety less than 1 is for failure, and more than 1 is reliable. So the you can say R minus S is called that R minus S. Resistance should be more than the load S, or capacity should be C minus D, like that. So we can always say that. So this is what I would like to illustrate, that the resistances. Are you able to see this diagram? Figure slide 18. Hello.
Yes, sir.
Hello. Yeah. Okay. Okay. So the resistances should always be more than the loads, and they're all distributions. So as I just mentioned, the factor of safety approach is always tricky, but then you can include, our interest is to say to what extent is the factor of safety value evaluation is correct. You can say, because it can have a bias. And what's the probability that the factor of safety is more than 1? If I say that it is 95%, then it's good. That's what it is. And the advantage is that it can take care of the construction costs, that there are some methods how it can be done. Say, for example, the probability of failure in a mine or a safety in a mine, there is a mines, nobody is there, so the consequences are minimum. But in a centrally located place in Vizag, the consequences could be very high. So you have to, we may intuitively go for higher factors of safety, but it may not be necessary. You can exactly calculate if you know the consequences. Say, for example, there will be a blocks, there will be a project delays. There are so many consequence costs. If you're able to have an idea of the consequence costs, you can come out with a proper safety. What is the required safety required? What is the required safety? So we do working stress method of design, which we don't want. This is what I was telling, that we'll have factor resistance, like the resistance should be always more than the loads. So we use some factors. So we always reduce the resistance, because say, for example, you have how do you calculate that resistance? It's based on the statistics. It could be 0.5, 0.8, it depends on the probability distribution, and even factored loads. It depends on the loads. So for example, you're designing it for 10-year loads, or you're designing for 50-year loads. So the factored loads will be different, like 1.2, it could be, otherwise it can be 1.8. So like that, even creep factors, anything, if you have data, you can always do that. These factored values are important. And so the advantage of this is that people are able to, it will lead to efficient design. That's what people have seen, because you can, even if you're like, I will show 1 or 2 examples on cost savings as well. And it is more perception of the uncertain factors, rigorous treatment, okay, whether it is for superstructures and structures, and the codes can be relooked at properly. And say, like, if our quality of control is not good in India, your factors can be put in there. You measure, see, like, what is the quality, like, you may have a poor equipment in India, whereas they have an automatic equipment in some other project. So they can really show that by taking some samples, or they need to have an experience on, no, I don't go for the same factor of safety because I have better equipment, because of which my uncertainty is quite less compared to the SPT test that they are doing, that some other company. So you can come out with this sort of numbers, and that is there in certain projects also in abroad. Okay, so this is what I was just mentioning, that the resistances and loads, so the probability of failure has to be minimum or 5%. I'll just go. Actually, people have come up with a basis, and I mean, what is basis? I will tell you. There's a, I don't know, are you able to see this figure?
Yes, sir.
Okay, so somebody should tell me so that I can go on. So the thing is, this is by MIT Professor Whitman, Lamb and Whitman. So what they did was that actually they took the data of what are the probabilities of failure of different structures, and how meaningful it is. Like here, they're looking at annual probability of failure. Like, say here it's 0.1, 0.01, 0.001 on the y-axis. Then the lives lost, 1, 10 million. I mean, lives lost and cost is there. Both lives and costs are here. And so they were looking at dams. So for example, dams. You can take it dams. Dams, here they got annual probability of failure. You should remember that. It's 10 to the power of -4. Okay. Like you can see that the dams, it lies between 10 to the power of -4 to -5. What it means is 1 in 10,000, like that, which is particularly for dams in a period of 100 years. If the dams fail, it's dangerous, right? So because consequences are quite high. So, and then their failure costs are also 10 to 100. Of course, in India, it could be more, and million. So they have marked it here. Similarly, mobile rakes, slopes, foundations. So you can see foundations, -2 to -3. This circle, then slope stability -2, mines -1. Then in the biggest in the mines, if the consequences are very less, so I know, of course, one should be careful. They'll have a lot of instrumentation and all of that. So even there, so this is how they got this in 1984. And that after that, there are a lot of improvements, and the people have come up with this number. There is another figure here, which will show about the same thing. The same plot is redrafted, and it shows number of fatalities due to dam. Actually, this is actually code on Australia, New Zealand Committee on Large Dams. Okay, based on this figure, many people have revised. Even in India, now we have to follow. I think you may be knowing about or they call DRIP. Okay. In fact, they're asking, I mean, I had to teach these courses on risk analysis. And unfortunately, in India, not many are aware of this, particularly in dams. So, because for them, in dam, dam risk analysis is very important. Here, so they're using this figure, and you can see that number of attacks due to dam failure, and the y-axis is like, you can see that -3 to -4. There is a region which is marked. That is called risks to be as low as reasonably practicable. It is called LRFD principle. Are you able to see this? Hello?
Yes, sir, it is visible, sir.
Yeah, okay. So this region -3 to -4 is the annual probability of failure risk that people have to design. They have to verify. Okay. So people have been working on this. Okay. So there are, what is that? You have how to calculate this probability of failure. I told you about you have a mean value of loads. They'll have a normal distribution. So it's a bell-shaped curve. And if you know the mean value of resistance or mean value of loads, like say, for example, the loads you always have, and you always have resistances, you find out the mean values and the standard deviations, you'll get beta. It should always be 2 or 3 or something, or the probability of failure has to be little low. So this is actually given by US Corps of Engineers. Okay, people working in the dams, they follow it, or even in regular code, they follow it. So that beta is in terms of 2 or 3, like I gave a table here. If it is -1, where the probability is the failure is 0.01, it's 1.28. But if it is 1 in 100, 2.33, 1 in 1000, 3.09. So for shallow foundations, deep foundation, you try to use this. The important thing we should realize is that this is a notional probability. Like, it is just to improve our understanding of behavior of structure and safety. Okay. It is not that absolutely that we have 10 structures and one should fail and all that. Okay. But it is a relative measure of safety. Better than, like, I cannot say if the factor of safety is 2 and 2, one is 2, the other one is 1.6. Which is safe. Somebody may say 2 is more, but I will give an example now in a little few minutes later that it is totally wrong, that idea. Okay. So we'll discuss how to measure risk, and you have all the calculation methods. Like I just mentioned one, there are first order reliability methods, Monte Carlo simulations, there are so many things. And what is acceptable risk or reliability? Codes are available, like US Corps of Engineers, Joint Committee on Structural Safety, they're all there. It's all, whatever people do in designs, it's already inherently done. Sometimes what is happening in some countries, you directly tell them about reliability, they may run away, right? There is a possibility, no, I don't want to understand this probability distribution, calculation and all. Tell me in a simple way. Then, so people have already built into certain, they will not know, but the people who make the codes, they know that these are the numbers that people should use in these conditions. Okay. So this is given by US Corps of Engineers, and this is given by Joint Committee on Structural Safety. I wanted to give an example of a foundation design and a marine environment. Say, I hope you're able to see this figure. 28 slide number.
Yes, sir.
Okay. So you'll have a question now. See, the thing is, what happens, there is a foundation design, and they have all the data of wave loads and all of that. And you have one flat one where it shows that, see, you can see on the x-axis factor of safety, on the y-axis probability density function. So the factor of safety here, it shows that it's 1.73. Okay, because this area below 1, I mean beyond in this less than factor of safety 1, it is higher. So the probability of failure is 0.02, means 2%. So 1.73, okay, is the factor of safety. So what they did was that after 20 years, they wanted to, because they wanted to rehabilitate the structure or something. They were trying to look at the loads and all of that, and then they again verified. Actually, it is from a standard book or a class. Professor Lacasse is a Norwegian Geotechnical Institute director. She's a top person in geotechnical engineering. She gave this presentation, which shows that. So when they measured, say this may be 1970s, and after 20 to 25 years, whatever is the time, they wanted to look at improved safety. So safety, factor of safety is nothing but resistance by load, right? Like our capacity by demand. Okay. So the that is 1.39. The resistance has the capacity has increased or resistance has come down, whatever, we don't know. But the probability of failure is 0.008. So according to which is better? Is design, does it, so since the factor of safety is now less than 1.5 or 2 point whatever, should we not, should we go for rehabilitation of the foundation or something? They went with the decision that nothing is required because the number one, the probability of failure is much lower because 0.008, whereas it's 2% here, it's less than 8 by 1000 actually. It's 2 by 100 here, right? So it's much lower, and they went ahead and they're okay. Why? Because in the olden days, the improved methods of testing analysis were not there. Now we have better methods of analysis, though the factor of safety shows that it's less, but probability of failure is low. So they went ahead with this consideration that it's fine. So a lot of examples could be given, like even in seismic stability of slopes and all of that. Like if there is a simple slope like this, the factor of safety variations are like I can plot the variation of factor of safety on a y-axis, whereas the earthquake coefficient 0, 0.1, 0.2, and so actually the code says that if you have a factor of safety of 1.5, it is fine, and but in earthquake conditions, if you include earthquake factor, it should be more than 1. Okay, that's a code, and we know that it is for a slope of about h is about 6. It is a small slope, and it's an example that is constructed to illustrate. We are trying to look at the factor of safety. If you consider earthquake, the variations are very minor in factor of safety, but when you look at reliability index, it's quite clear. Like, say for example, for a 0.2 earthquake coefficient, the slope will fail, but the conventional methods of analysis will show that it is safe, which is a tricky thing. So like, so whereas you can say that in the say 0.1, they clearly show that the factor of safety is very good, but the moment it is 0.2, it could fail. So these things, of course, it should be always backed up by field measurements at times, but this just gives an idea that reliability analysis is quite useful to understand. Yeah, this is about pile loads tests. In literature, you have many examples that say for example, if you're looking at an allowable settlement of 0.02, the thing. So you will get varieties of loads, like which one you have on the same type of soil, you have 4 tests done, and the load varies from 33, 30 to 52, 100, right? 33, 30 kilonewtons to 52. So which one I should take? So this is actually in a literature available, and in a denser sand, and so why is that? See, there is nothing wrong in the testing, but it's only because it's inherently variable due to geological processes. So you have to consider this. How do you do this is a question that we'll see. So this reliability analysis we already discussed. Okay, so we also have a lot of methods to do that. Like one simple way of doing things is that you know the capacity, how to calculate factor of safety. So with you have say 100 C values, 100 friction angle values, so you can calculate 100 factors of safety, and that is using then you tabulate them and find out what is the probability of safety being more than 95. You take it, and then corresponding to that you calculate the even the factor of safety, because you can calculate even the factor of safety corresponding to 95%, because all the factor of safety you will have a distribution, like I showed you in the previous example. The factor of safety is a distribution, so corresponding to 95% you get, and whether it is 1.2 or 1.5 or 2 or 3, don't bother, because that gives you the probability that it's 95% satisfactory. So that's the way. So that is called Monte Carlo simulation. Actually, it is now you can do in 5 minutes. Actually, you don't need to work too much. You have in a Excel or MATLAB or something. You can even generate. I will show you that it is simply in a simple way. It can be done. There are so many ways of doing it. Like so, normally I told you that the limit state function is called factor of safety equation. So then we are trying to calculate reliability index. Okay, this is a simple thing that one can calculate. Okay, either it is, there are different methods, like if it is a simple simple calculation. So for example, if the cohesion of the soil is 10% variable and friction angle is 20% variable, what is the variation factor of safety? You also have a simple methods of calculation, like using Taylor series method, like we studied in engineering, that if I make a 10% error in chain, what is the error in total measurement? Okay, like we studied that type of problems. These are the same thing, that error methods. Like, so our objective is to reduce errors, right? So we have methods to calculate the reliability index, which tells you the how away you are from what is called the failure or the limit state. So we also have some terms called sensitivity analysis, like what are the factors that will to which this factor of safety or safety is sensitive. Like sometimes in some cases there will be 5 to 10 parameters. You don't know what to do. You calculate everything, but 10 parameters you can't always do. So say for example, in a building, there could be the contributions of the deflections at a point could be due to many other loads, right? Combinations and moments and all of that. You're trying to calculate, because you can't do every time the same calculations. It becomes cumbersome, even in a finite element analysis. Then you have to find out which are the critical parameters that will only I should consider. Maybe 4, 5, 6. Like say for example, there is a bending moment or a shear force which is critical at a particular point. Which are the factors that are affecting that has to be known. Maybe there will be 100, but I don't need 100. I know only 4, 5, 6, which are in there, because that is called sensitivity analysis. We call it a sensitivity analysis because their contribution of large somewhere, in the top floor, if there is a loading happening, it may have not even 1% effect on this. So it's okay. So that is called that. So we do that, as I just mentioned, about Monte Carlo simulations, and that's a very useful technique. So I just mentioned about target reliability index or probability of failure. I just discussed. Essentially, it can be based on the codes that we already have. But if you, for a new project, say for example, you're trying to build a structure in a coastal area, or a sea erosion problem, or anything, how do you do this? So you have to understand the consequence of failure. Sometimes the problem with the codes is that they're all general, and if you do follow blindly codes, if your structure fails, then it's a shame, So we want to see that the consequence of failure are minimum. So we have to understand the consequence of failure, and if you do a little bit improvement, what is a change in reliability also we have to find out, because we have seen in many of the rehabilitation projects, Yeah, you want to do a lot of rehabilitation and it needs so much, but there could be some things that may, if you repair this, they may contribute to 90% improvement, but some others 5%. So you ignore that. So like that. So you can always do that, and you can always, it helps in code making because it's very important. And there are different limit states, like we know the strength limit state, serviceability limit state, and fatigue and fracture, like, and then extreme event limit states. So for example, under certain conditions they should not fail, right? So there are many other things like primary components and secondary components in a system, or in any engineering system we have, which are the primary inputs and the secondary inputs, and so that can be done. And there will be load paths, single load, single paths, load, multiple load paths. Loads coming from different say for example, loads can be so much, right? Like live load, wind load, all that combinations. How do you do that? Then single redundancy. See, why this thing is important is that you should understand how the loads act on the systems, and we also have to have necessary redundancy. This is very, very important. See, redundancy should be there, the extra, but how much extra? If you just don't know, then our designs are meaningless. So this, say for example, in a pile foundation design, you have to calculate how many number of piles extra are required to have the same level of reliability. It's not that factor of safety will not help you here. Actually, it is ridiculous. In fact, I don't mind mentioning that. See, you need an extra number of piles that will give you that thing, 0.99 or whatever. See, you have to take care of the load, and how much. See, if you take this much, say for example, 5 piles, if you put, what happens to reliability? 6 piles of this diameter, what happens? All of that can be worked out, and then you come out to the redundant factor where what is the number of piles? Say, like I 0.9. There is reliability of 0.95 and there is reliability of 0.99. So reliability cannot be more than that, right? So 0.999 it can be. So how many piles I need? That needs calculation, and that can be done. But if you just simply use some factors and try to do, then it could be tricky. So the other thing that we need to understand is that, like element and system reliability. Okay, so it is not, there is one pile is there, so it should be reliable, but as a pile group, it is a system, right? So it should be completely reliable. So like that. So you need to understand element reliability and system reliability, because, say for example, you take the case of a bridge, everything has to be reliable there. Foundations has to be reliable, then the superstructure has to be reliable. The approach road to a bridge also should be reliable. Okay, if the approach road to a bridge is not reliable, it's a bumpy road, it's not useful, because system reliability, the use of the bridge is minimum. We should also understand the new designs and existing designs. You should understand the ductile and brittle material nature, the behavior of materials in the system. Like, say for example, steel is there, concrete is there, soil is there, geosynthetics are there. There are so many materials because the strain compatibility, like all of these materials will reach failure in different ways, and we know that, but the strains should not be too different in otherwise it leads to failure. Strains, there should be a strain compatibility, right? And strains in the concrete should be same as strains in soil, or even the reinforcement or anything, like whatever you want to say, reasonably some numbers which should not lead to slipping. Like we see the slip of the foundation, slip of the materials, pull out failure. We don't want that. So you can always understand the nature of materials is also important. Is it clear? Are you following? Hello?
Yes, sir.
Okay, thank you. So there are primary component, secondary component, new design. This already I discussed. I'll give some examples of I've been working. There are so many. At least all my PhDs are on this because I find that it's very interesting, and nobody is really concentrating this, and it's quite interesting. This is an a shallow foundation example, like if you have a factor of safety of 3, shear failure criteria in a particular case, I just want to try to give an example that, C and phi and all the variations, I'm not giving it here. And I'm only trying to say what happens. So the safe bearing pressure with the factor of safety is 322, because the 967 is you got from C, phi, gamma, and all of that, and got the number 967. Then you also go use a settlement criteria, and so 25 mm or 40 mm or 50 mm, what is the allowable safe pressure? So it could be, we know that the settlement is increased, bearing pressure increases, it could be 257. So in this case, you can say that whichever is the least we take, and we try to give in a deterministic sense like this, for depending on what settlements you want, it can vary from 140 to 257, because of these two, 322 on this is lower. So the reliability index you can always do, like as I just mentioned, C and phi, and C and phi values, they're all variable, right? And so you can always calculate reliability index. Okay, I told you reliability index can vary from 2 to 3. Okay, so for a number of 3, see, there are two things here. The soil is spatially variable. The other one is without variability. Like without means, like I told that there is an autocorrelation distance and all of that. That is, without spatial variability, it is little higher, 270. But with spatial variability is better. Always the thing is that if you consider spatial variability, it always is higher. And here also settlement criteria you get. So what it shows is that you will get a 226 for 50 mm could be the allowable pressure. So one thing you should also important is that this basis of 25, 40, 50, you should really come out with proper numbers. You could see that they're considerably different, like 25 to 50, 124 to 20. Even in the previous case also, they're different. Like, so 257 we said here, but we said 226 here. So the allowable pressure is little less. Hello? Hello?
Yes, sir. Yes,
Yeah.
sir. You are audible.
Okay. Okay.
Yes.
Thank you. So I will also, this sort of things one can calculate. So I will give some examples of piles. But then, the thing is, see, you have a lot of design methods, and then one can use a numerical analysis also. Like, say, this is an example of a numerical analysis, which we did. I should, one of my students, he is in IIT Bhubaneswar, Mr. Sumanta Haldar, he did all of this work. And so actually, like, see, the way that numeric analysis, use what is called Praxis or finite element, because the thing is, it is much better than conventional methods. The conventional methods are designed, they have assumptions and all of that. Whereas in a numerical analysis, you don't have so many issues. You simply load the system and then you use appropriate properties or even variability. You can introduce variability also. And we did that type of analysis, like you have a pile, and so we're able to, in fact, I was mentioning about random field. What it means is that if point-to-point variations are too much, then it is, it is highly erratic. So you'll have more weak zones, but if it is uniform. So for example, if the soil is uniform, the weak zones are less. But if it is, if the standard deviation or coefficient of variation is high, it is more weaker. So the planes of weakness will be, you can really identify. In fact, we're able to do that in a certain problems that will give you an idea of, say for example, increase in coefficient of is for an undrained shear strength of soils. Increase in COV is, it shows erratic nature of soil, more weak zones. at low values of correlation distance, means they're point to point, they're very nearby. So the soil is erratic. But if we increase the distance and then get the numerical results, then you'll get a better result. Then what we do, I will just show. Yeah, we did for a vertical loaded pile and all of that. We did some numerical analysis. Yeah, this is the interesting thing. See, the thing is, depending on the, you can always numerical, because you have numerical simulation runs. I told you the earlier in the field, you are doing 4 tests or 5 tests. Okay, that for the a few 5, 6 tests are okay, that's fine. But then that can be used as a basis. And ideally, we need to have at least, to satisfy normal distribution, we should have about 30 tests to make it reasonably all right. So you can construct some upper bounds and lower bounds and do a Monte Carlo simulations, like it is here. So you can even do that in numerical analysis, and you'll get, see, without even doing testing, you can get results of 100 samples, okay, 100 or 1000. It can be many. Like I think I'll show you a previous result. Like we did that, sample size is 200 here. 200 samples. And if you take low samples, what happens? The standard deviation will be low. It is like, if I have 5 samples, 1, 2, 3, 4, 5, the 1, 2, 3, 4, 5 average is different from 1, 2, 3 or 3, 4, 5, right? We know that average and standard deviations are different. So I cannot say anything. But as the sample size increases and it becomes constant, then it is very clear that the standard deviation is same. So measured loads, so you can get some error. But that's the reason, by only doing 1 test or 2 tests, you cannot decide anything, right? So because everything is variable, you do a specified number of tests and look at this sort of numbers. Like what happens if the if the number of tests are increased. So this cannot be, if you want to do 200 pile tests, I cannot do 200 pile tests. I can do only maybe 10 or whatever number. Try to understand it and try to see that they're all into these numbers, and others you can numerically generate, right? And get the overall response, because we assume that the pile test results numerically are giving the actual picture, because you already validated it with the field result. You can get this, and you don't worry about applying factors of safety blindly. Look at these trends, then calculate the allowable loads. See, you get a deterministic curve, you get a Monte Carlo simulation, find out the average. That may be better than the just trying to have a deterministic curve, because the averaged curve from Monte Carlo simulations will give you a correct picture, because it's an average thing, whereas a deterministic test is a 1 test or 2 tests maybe. Okay, but the Monte Carlo simulations, they'll give a wide range, and it is still an average, but it will give a correct picture. So that will tell you how much of correction you have to apply for a particular number. So one can do a lot of studies on this. See, normally, say for example, ultimate bearing capacity, right? Ultimate bearing capacity is we have a number, or a deterministic number. Then how much it should be reduced? Should I have a factor of safety of 3 or 2.5 or whatever? How do you get it? I cannot say arbitrarily. Okay, so that's what we do, right? Ultimate bearing capacity, say for example, 5 shallow foundation, 5.14 cu. Is a footing resting on a soft soil, or if you take it deeper, it's different, or if you have a pile, it's 9 NC, right? All of that one can do, and so deterministic value is known, but how much should be the factor of safety, how much it should be reduced, cannot be it cannot be arbitrary. Like I cannot use a factor whatever 3 or 2 or something. It can be done as per codes. You can say it's codes, but if you do a reliability analysis and show that, suppose, for example, the soil is fairly uniform and using a factor of safety of 3 gives you less load, then it's not correct. If you're able to prove that by proper testing, proper analysis, if the factor of safety can be reduced to 1.5, you will be benefited, right? There's a pile diameters will change a lot, and your cost of the project itself is completely impacted. Do you get this point? Hello? Hello?
Yes, sir. Yes,
You
sir.
understand? You understand this? You're happy with this observation?
Yes, yes, sir.
Who is that? Yes, sir. I'm very happy to listen to you.
Krishnam Raju.
Krishnam Raju, great, sir. Okay, so we'll meet some. So the thing is that we can't use this arbitrary factors of safety. You should know how safe is safe, how much money is valuable. It's like betting, right? So it is like that. So you have to apply these partial factors based on the variability. You can't just 20% variable, 30% or 50% variable. I can correct it, and I want to be very safe. It's not, and then you can even build in other things also. So in fact, see, the idea of failure is something that one should understand, that slip circle always passes through weak zones, right? Any material, even the flow happens through weak points, or like that. Soil is variable. It is not like you read in textbooks that slip circle will be on either side equal, right? One side, other side. It will not happen, because footing is going to turn on one side and fail, right? It will have one direction failure. It will fail. It will not fail. So in which direction it fail? How do you say? Wherever its soil is weak, it fails. How do you say it's weak? It only you can say it's weak. It's because coefficient of variation is higher there. Then what happens there? Because the strains are higher. Strains will be more there. So strain accumulation happens, and finally it happens. It fails that side. Why failures? Like you could have seen that failures only happen at some places, not all places. Like infection happens only in some places, not all places. It's like that. So unless things are like weak zones, right? So that's what I want to say. The same logic we did for laterally loaded piles, okay? And this all published in ASCA, Geotechnic, and there's so many journal papers, okay? The same thing like average, that say you try to calculate using simulations or some calculations and try to find out the mean value standard deviation. It's like you're not confident in the first 3 or 4 trials, but you understand completely the behavior and try to find out the what is the extent at which they can become constant, and then find out their mean value and standard deviation. That's what it means. Then you are very confident of your design. Yeah, same thing for lateral loaded piles, that we did stochastic, means that variable analysis, and deterministic, what is the difference? So we always clearly get that depending on the length of the, the deflection limits and all of that, you can always talk about allowable deflections and what do you get and what should be the partial factor you have to use. You can get it, because in a given soil, the thing is, when pile foundations are so expensive, in fact, I know many cases, piling contractors are very happy, but owners are not happy, designers are not happy. Why should I have this situation? I myself had to struggle in a couple of cases, because the pile contractors insist only on, they make a lot of money. So they don't want to improve quality of testing, because quality of improved testing leads to more economic in design, which means that the number of piles are reduced, whether it is Vizag or whether it is Kochi or Mumbai. I'm seeing the same trend. So this is a pity that we have. We need to understand that value of information that goes into this is very, very important. Yeah, so the same thing, that how this information can be used in design. Yeah, so these are all some results I just wanted to share, that how do the failure happens and the influence on the formation of failure. Because as I said, you apply load, but the weak, wherever there's a weak zone or weak strata, the failure starts from there. Then you keep on applying load, it develops, and then it envelops. And if the conditions are more conducive to failure, things happen. So that way, this you can capture in a numeric analysis and even a probabilistic analysis properly and take precautions. Like, so for example, you do grouting or whatever you want to do, and you can simulate that process also, right? So I just want to tell you about vertical, there is, the spatial variability of soils can be considered based on proper reliability analysis, whether it's vertically loaded or lateral loaded. And I just also want to bring to you maybe another 5 minutes I'll take, because I thought I'll leave it for questions. Otherwise, I have a lot of information. Even retaining wall design, we have different types of retaining walls, cantilever, reinforced soil structures, and all of that, static and dynamic conditions. See, in the reliability calculations, there are different levels of design. One is called, as I said, LRFD. That is followed in the UK, or actually they call it partial factors code. Even in Federal Highway, they use this. That is a level 1. Factor of safety is a 0 level. I want to make you I want to make the statement that it is actually factor of safety is because there is nothing that you're not considering uncertainties, and it is okay. Maybe we have been doing it, but when you have so much data, so much of quality control required, methods are different. Then you have to use better methods. So we use level 1 called semi-probabilistic methods for simple calculations. Approximate probabilistic methods, I just showed, like simulations and all of that. Then even fully probabilistic, what it means is that the optimization, costs and all that, you will get really a very good benefit. At least you're sure what exactly you're doing. That's why, when there is so much of data analysis, cost, sustainability analysis and all that, if you do that, you'll get a very good picture of this whole design. This is, I just want to, retaining wall failure. You have so many limit states in the retaining walls, overturning, to failure, shear failure, eccentric bearing capacity, and all of that. If you're able to do, there are so many parameters also, so there are so many parameters and all of them are variable. And I want to show you that target reliability index, if you change different, reliability, when there are so many failure modes, you'll have different reliability indices. How do they change as a function of, the dimensions of the retaining wall, heel by length of the heel by the height of the retaining wall, something like that. So based on that, we're able to get optimum dimensions for retaining walls actually. Okay. Based on all of these things, we're able to get optimum dimensions. And so it's a very interesting case that you open any book that like Bowles book or anything, they'll give you some dimensions. Okay, you take 0.3h, 0.4h, something like that, or heel length, this thing. But we are looking at based on this, say for example, the length of the toe, length of the heel, like 0.24h, all of like that, so we are able to get that. And what we did was that we found that if you use this design, okay, like, in fact, I have given here Bowles book, it is there, Das book, it is there. There are so many papers. And if you do a reliability analysis, you will get 30%, 35% reduction in the area of concrete actually. Okay, percentage savings in the area of the retaining wall for different heights. Okay, what it means is that the reliability analysis, like, the reductions in cross-sectional with compared to conventional design specifications are 7 to 27%, which is good, right? So what I want to say is that we have to understand what is why should we blindly specify? Like, I have seen in some case where they followed the specifications, but still the failure happened. So it doesn't mean anything. The design has to be correct. So maybe I'll stop at this stage. It's 5:24, and I'll open it for questions because I have a lot of information, but I think I could cover some shallow foundations, pile foundations, and some given idea of retaining wall. So I'll open it for questions at this stage. Tell me, sir. Yeah.
This is Krishnamraju, sir.
Yes, sir. Tell me, sir. Yeah.
I am fortunate that I have attended Dayaratnam Garu's lecture on this.
Oh, great. Oh,
maybe
very
around
nice.
25 years back when I was studying MTech in Andhra University.
Yes, sir. Very nice.
Okay, he at that time we know only partial safety factors for 1 or 2 in our codes.
Yeah. Right.
But he has shown partial safety factors 5, 7, 8 like that. Maybe at that time, whatever you are referring, they were studying.
Yeah.
till today that was not materialized, I think.
No, they're not. Nobody's interested. No, Nazi, like, people of 10, if only 1% or 2% knows, people know, then, they're not interested also. Many people, I see that, in the India, say, for example, the federal highway codes, they have improved. Though they don't know much about probability, they have taken the help of experts and they corrected it. And then codes are continuously evolving because money, projects, everything is continuously evolving. Whereas in our IS codes and IRC codes, it is all they're not serious. So that is a problem. Yeah.
Yeah. One more point I want to tell you that the reliability for foundation or superstructure or any, the concept is same, I think.
Yes, yeah, perfect. Anything, even electronics also, they're using, say, even in your computer system, their reliability analysis is -6. See, you don't want your computer to shut down in the middle of a presentation, right? It's 1 in million there, that is everywhere, but it is a manufactured product. And unfortunately, so that is there. Yeah.
One example I want to tell you.
Yes, sir.
One 6-story building was designed for gravity loads only.
Oh.
That building was sustained for a recent wood in Visakhapatnam without alarming effect.
Okay.
That building was not designed for wind.
Okay.
Real test. What is the reliability? Then when I have asked one institute, can I provide the wind design for such buildings, because 5 meters per second is the basic wind speed, whereas around 65 meters per second was measured. Okay, then that institute has mentioned codes are recommending, so we have to do. That is the
no, you can. Yeah, actually, what you pointed out was very right. In fact, I showed you one figure that was prepared by back calculation of reliability. Given that the structure is standing, the loads, the loads and forces, the resistance also. So you can calculate reliability index.
Yeah, now we are working out on that.
Yeah, for existing structures and all these things. So we can avoid failures. The advantage is that if you do a lot of some sincere work, you can do a lot of work. Yeah.
I think the academicians may take up the designs of the existing structure, what may have designed, let us forget about, and then rework it out and reliability.
Correct. I mean, the owner should allow they definitely should be done.
Oh, if it is academic purpose, they will allow. But if you say that,
no. Even actually, let me tell you one thing. See, it's not about academic thing or something. It is actually, if you look at US or other places, this came because the business. It's all business. See, you want to do good quality testing. You want to make good business, not in any other way. So it is driven by business needs. Like even in why the quality control in many other things have improved a lot, but only in infrastructure is very poor because it is not there. You take road work. The IRC codes are not very good. Then many things are not okay. So, but we have not really contributed anything. Maybe structural engineering to some extent as a building design, because the quality, quantity, everything, that they are very okay. But other cases, it's a problem. So there is a question here. As we have a lot of restrictions, either in boundaries and retaining walls for residential and commercial, how can you use this for a reliability analysis? Can be used for anything. Just it's not about restrictions or anything. You have to understand the failure. They design the conventional design, then look at all the boundary conditions and forces and all of that, and they can do it. It should not be a problem. Okay. Yeah. Any questions further? So, Mr. Gautam, you have any question? I don't know. I'm just asking. Arun Vajrapu, you have any questions? Because hardly 37 people are there. You can pick and. So, Gautam, Arun are not there then. They have switched on and left. Okay. Mehirlal, I don't know.
No, sir. All are there.
All are there. Then why Gautam is not answering?
Some are keen on listening on.
Oh, they don't want to ask anything.
Mihir, several posts we'll see with that name.
Okay, on the lighter side, yeah. Because in my class I keep asking every 10 minutes I stop, because otherwise they'll be very busy. So you want me to continue? I think it's okay. I think people should not get bored. I gave some idea of reliability analysis. And Professor Reddy, you have any questions? I don't mind. I'll be happy to answer, because you have a lot of
actually this reliability analysis course is there in MTech structural engineering program at our university. And for our geotechnical students, as elective, they can opt for it. That option is there.
They're opting for it.
That's why most of the structural engineering students are exposed to this area. I think in other institutions also we need to adopt this, because now Euro codes and all, if you see, reliability based design, they are suggesting slowly our codes. I think even IRC is also.
Yeah, it's very late already. They should have done 10 years back. That's the problem.
Still they are going for it, sir. It is a good change.
No, they're not going. IRC, I know IRC, because I'm interacting with them directly. So
draft version.
No, they have some numbers.
Yeah,
they have some numbers.
IS 456, they are going based on performance design.
Yeah.
So any more questions from any of the participants? Particularly the younger generation, right, who have confidence, right, in probability theories and all, right, they can take up their research problems in this area. It has a lot of potential. The very reason for not seeing many failures in Visakhapatnam during Hudud is just because of high factors of safety that are used not only in taking material strength, but also in evaluation of bearing capacity of soils. So that's why the probability of failure will change if the loading condition varies significantly from what is adopted for design. So the factors of safety are protecting. Instead, in large projects, it is always advisable to go for more detailed investigations and to adopt reliability based design, considering all uncertainties into account. So I have posted the book reliability analysis. Structural, the title is Structural Reliability Analysis and Design by Ranganathan.
It's a very good book. Yeah, it's a good book.
So those who are interested can have a copy of it and try to go through it. The subject matter is covered with number of illustrations. You will find it.
Very good book. It is. Actually, he's a student of Professor Dayaratnam. Okay. So he's very good. Actually, he is a good book for Indian conditions. He takes a lot of data of wind loads, live loads, and all of that. It's a nice book, but you can apply to any area. Yeah.
Most of the times, engineers will keep coming to us with some old soil test report. CN5 smudge bearing capacity is say 25. Now again for confirmation we have tested, we got 23.2. So if they understand this reliability based design approach and all, they will not be worrying too much, because that is not a big issue.
Yeah.
But people worry a lot, even if they notice that in one of the soil test report on one sample, if it goes below, they'll be worrying a lot.
Not only that, they'll cook up. No, that is other problem I see. they'll cook up. So they have to understand that they don't need to cook up and have variations and understanding. Yeah.
And also one more unknowingly good thing what structural people are doing is whatever bearing capacity geotechnical consultant is suggesting, though they are taking wind load or seismic load into their design, and they are not considering the allowable permissible increase in bearing capacities. When they check against the base pressure from the footing, they are comparing against the recommended bearing capacity one. Depending upon the foundation, if it is raft, if it is isolated column footing, if it is pile foundation testing on hard strata. IS 1893 is allowing for considering increased soil bearing pressures that they are not taking. So that's why even in the worst conditions, also structures are standing.
Okay.
But actually, all the designs need more refinement, because structural people for their loads they are using factors of safety, and on soil parameters we are using factor of safety, and finally we should see what is the reliability index and what is the corresponding probability of failure. One should look at it and accordingly economize, made adjustments in design. Sir, if there are no questions from the participants, I thank you very much for covering various aspects of reliability-based design, its significance, and what are the areas people can think of going for it. So thank you very much, sir, for sparing your time.
No, it's a pleasure. Thank you very much.
Giving a highly informative talk. So participants, those who are interested, if they have any doubt later stage also, they can contact Professor Babu sir.
Yeah, sure. Perfect. So thank you very much. Then I'll take leave, Professor Reddy and the participants.
Thank you.
Thank you all. Have a good time. Bye.
So I thank all the participants for their active participation in the afternoon session. Hope all of you might have enjoyed the lecture and gained at least some information and idea about reliability based design. So whatever partial factors of safeties that are being used on concrete strength, right, steel strength, and whatever factor of safety we use in bearing capacity estimations, slope stability analysis, indirectly those factors of safeties refer to what is known as probability of failure. Right? So one should understand that. If you are deviating from that specified factor of safety, you should check to what extent the probability of failure is changing. Right? So looking at that little deviation, if it is there also, nothing will happen to your structure. Okay, so during your leisure time from your library, you can have a look at the book, right? That is Structural Stability Analysis and Design by Ranganathan. Okay, so that's all for now. We will close this session now, and tomorrow we'll meet again for the lectures on well foundations in the morning and foundations in expansive soils in the afternoon session. Okay. Thank you.